polynomials for non-Hermitian random matrices.
Okay. Let me start off by thanking the organizers for the opportunity to speak at this wonderful meeting. And we've already heard a lot of nice things about Jeremy, so let me just add to that just by saying that, Jeremy has had a very positive effect on my professional life. And he was chair when Toronto hired me, so, thanks for that. That's pretty good. So hopefully, in this talk, I can help convince you that this was a good idea. Okay, so I'm going to talk about random matrices and not KPZ. So when I told Jeremy this, he said, "Oh, that's fine." So I took that as a green light, so we'll go ahead. Okay, so this is joint work with Giorgio Cipollone, who I believe is in the audience here today. So we're going to be looking at random matrices X, and they're going to be little n by little n random matrices, and their entries are all just going to be IID random variables. And it's convenient to take a scaling in which each entry is of order 1 over square root n. So in distribution, each entry will just be 1 over square root n times some fixed random variable chi. And I'll be taking the random variables to be complex because this is the technically simplest case.
You read a little bit.
Sure. So chi will be centered, and the real and imaginary parts will be uncorrelated, and their variance will be the same. And the overall variance of chi will be normalized to 1. Okay, so one of the most natural quantities, perhaps, when you're looking at a matrix is to consider its characteristic polynomial. So that's just the determinant of x minus z. And what I'm going to do is I'll take an absolute value because I want to look at the size of this matrix, of this quantity. And it's also turns out to be convenient to take a log here. And then I have to subtract off what its leading order deterministic asymptotics are. And when you have a matrix of IID random variables, thanks to the circular law, we know that the eigenvalues, their empirical distribution converges to the uniform measure on a disk of radius 1. So that means that this leading order deterministic term is just going to be an integral of the logarithm of the absolute value of x minus z, where here this is just the normalized area measure of the disk, right? And so let's call this field, because it depends on z, psi n of z. Okay, so in general, what one expects for psi n of z is that it's going to asymptotically be a Gaussian process, and its covariance structure is as follows. So the covariance of psi n at 2 different points in the unit disk, to leading order, it's going to be equal to the logarithm. And I write it in this funny form. So this is going to be log of a small number, so I put a minus sign in front to get something positive. So it's going to be the logarithm of 1 over n to the 1/2 plus the distance from z to w. And of course, there's some lower order terms of constant order. So in particular, maybe this is even a little one. In particular here, right, if z and w are the same, then this is going to give us 1/4 log n if z is equal to w. Okay. So the fact that this variance is diverging on the diagonal, this reflects the fact that psi n is not converging to a random function, but it's converging to a random generalized function, and that is the Gaussian free fields, which of course is a generalized function that you can make sense in, for example, Sobolev space of negative regularity. And this was proved in the case of the complex Ginibre ensemble, which is when chi is a complex Gaussian random variable, and extended to the more general setting above so this was proven by Brian Ryder and Alan Virag, and was extended to more general random matrices by Cipollone, Erdős, and Schroeder. So here, let me just say that the Ginibre ensemble, that's the specific choice that chi is Gaussian. So now, what this logarithmic correlation structure, what this means is that this field, psi n of z, this is falling into the class of what are called log correlated fields. And one of the central questions in the field of log correlated fields when you have such an object is to determine what its maximum is as n tends to infinity, to determine these asymptotics. So by analogy with other log correlated fields, such as the branching random walk, which I'll introduce in a moment, there's a general prediction here that if you look at the maximum of psi n of z over the unit disk, then to leading order, this is going to be 1 over square root 2 log n. And then there's a sort of 3-term asymptotics, where the second term here is minus 3/4 1 over square root 2 log n. And then there's a random variable sitting here that's of order 1. And is supposed to converge in distribution to something that may or may not depend on the model. Okay. So let's just back up for a second and try to understand where each of these terms is coming from. So what I claim is that this leading order term first, this can just be guessed by considering a simpler case where you have n independent Gaussians of variance 1 over 4 log n. So here in the logarithm, we have 1 over square root n plus z minus w. So what this suggests is that if you look in, if z minus w is about 1 over square root n, then this is going to be highly correlated. So this should kind of behave like maybe 1 independent Gaussian to leading order. So in particular, in the unit disk, every ball of radius 1 over square root n has its own Gaussian that's sitting there. So that's volume 1 over n. So there should be about n Gaussians with some correlation structure, but that's sort of the that's the cardinality of how many things we're going to be considering, right? So, if you're just doing something like a union bound, you want to estimate the probability that this max is bigger than x, right? So if you do a union bound, there's n because this is how many Gaussians there are, and then we basically have this Gaussian tail, and then the denominator goes 2 over the variance. So we have 1/2 log n. And in order to make this order 1, this just tells us that we should choose x to 1 over square root 2 log n. So that's essentially where this leading order asymptotic comes from. So the first order term, that's basically the same as if you didn't have this log correlated structure, but instead you just had independent Gaussians. So where you start to see the log correlated structure is in the second order term. So if you had n independent Gaussians, a variance 1 over 4 log n, then instead of a 3 here, you'd have a 1. So this is where the log correlated structure actually comes. And in the independent case, this would just converge to some sort of Gumbel distribution as well. Okay. So the theorem that I'd like to discuss today is as follows. And so for our psi n, we're able to show this leading order term here. So we're able to show that the max over the unit disk of psi n of z is equal to 1 over square root 2 plus little o of 1 times log n with probability tending to 1 as n tends to infinity. Okay, so this is our theorem. Now, there's several precedents for our theorem in the literature. Okay, Lambert, he proved the same thing, but for the special case of this complex Ginibre ensemble. So that's when, again, the random variables have a Gaussian distribution. And in this case, there are various determinantal formula available, which allows you to do many computations, essentially, of the Laplace transform of psi n of z. But these kinds of formulas are not available to us in our more general model, where we're not assuming that the entry distribution of our random matrix is Gaussian. Another precedence before our work is the work of Bourgaud, Lapato, and Ofer-Zeitouni. And then they found the leading order asymptotic for general Wigner matrices, as well as 1D beta ensembles. So the Wigner matrix is just the Hermitian version of our matrix. Here we're looking at non-Hermitian matrices. And in the 1D case, there's additional interest in this quantity due to some comparisons with the behavior of the Riemann zeta function in number theory. And then one other related work is the work of Lambert, Thomas Laplace, and Zeitouni. And what they did is that they did the 2D Coulomb gas with a Gaussian potential. So specifically, for the complex Ginibre ensemble, if you look at the joint eigenvalue distribution, then this is going to be, a measure on C to the n. And it turns out to have a very explicit form, just as a Coulomb gas in a Gaussian potential. And one thing, there's an inverse temperature in the Ginibre ensemble. This inverse temperature is 2. And you can allow this to vary. And this is the model that they studied. And they also obtained the leading order asymptotics of the analogous quantity in that model as well. And then quite recently, Brian Ryder, Luke Pylon, he generalized this result to non-Gaussian potentials as well. So there's many related works to this that, of course, ultimately use very different methods because we're looking at very different models. Okay. Yes.
This non-Hermitian case, is there also some interesting information in the phases? So you took absolute value here.
This I have no idea. I guess it would require the choice of a branch of a logarithm, and I'm just not too sure what you would sort of. Yeah, so this, I don't know this question, but it's a good question. Okay, so what I would like to do is just tell you a little bit about the proof of this result. And for this, what I'd like to do is discuss one of the most central models of log correlated fields, which is the branching random walk, or what's also called the hierarchical Gaussian model. Okay. So in the branching random walk, what you do is you have a binary tree, which I'll just draw a few levels of. And this is a full tree, so it goes all the way to the bottom. And each edge will get an IID random variable, and they'll all be normal random variables that are centered and have variance 1/4. And here I'll put log base 2 n levels. Now, what are the random variables? At each of the leaves of the tree, you put some random variable, which is just going to be, the sum of the edge weights along the path that goes from the root of the tree to the end, right? So if you had another one down here, then, this might be the value of some other leaf of the tree. Okay. right? So this quarter is just chosen so that the variance of each of the Gaussians at the end of the tree is looking similar to our case up there. Now, a priori, it's not quite clear that this is some sort of log correlated process, because I haven't shown you some sort of log and some distance. The easy, since there is this branching structure, if I just tell you that there's a logarithm in there, it's probably pretty believable. One way to see it is that you can compute the volume of the number of leaves such that the covariance with another guy on the end is greater than or equal to some macroscopic fraction of the variance. And in this case, so here R is some parameter, R is some parameter between 0 and 1. And this set, this is going to be to leading order, some mesoscopic fraction of the overall number of random variables. So, the number of guys that have a covariance that is some macroscopic fraction of the overall variance, this is going to be some mesoscopic set, because here, since this is log 2n, there's n guys at the end, right? And there's going to be some similar thing here where the volume of all the z such that, their distance from W is like n to the minus alpha is going to be some mesoscopic fraction of the overall volume of the unit disk as well. So in this way, both of these processes can be seen as analogous. Okay. So there's a few salient features of the branching random walk, which are sort of the main things you're looking for when you're considering other log correlated fields. So the first is that, you have this dichotomy between, independence and, perfect correlation. So what I mean by this is that, for these two guys down here, right, as you follow the lead, as you go down this binary tree, of course, the increments above the point where they split, those are perfectly correlated because they're the same increment. And below the point where they split, then you have the perfect independence. So this kind of dichotomy is one of the things you need to look for in another process that you might be analyzing. And then the second thing is sort of this idea of that you have some sort of multi-scale behavior or multi-scale decomposition of your random field. So what I mean by this is that, level by level, we are building up each of the random variables, setting up the leaves of the tree, first from very large global increments, and then finer and finer ones. And sort of all of these increments are the same order. So basically what I want to do is I want to explain to you how we're able to uncover this branching structure in our random matrix ensemble, which will allow us to prove this theorem. So that's why I'm introducing this branching random walk. We want to find where this branching structure is in our model. Okay, so there's sort of two things that really save us and make this problem tractable. The first is that this problem is secretly a problem about Hermitian random matrices. And we have to use a certain hermitization of our model. Okay, so remember what we're looking at is we're looking at the logarithm of the absolute value of the determinant of x minus z. Right, so I can square this quantity here and put a square root in front and still get the same, put 1/2 in front and still get the same thing. Then of course, what I can do is I can write this determinant here as the product of the determinant of x minus z and the determinant of its conjugate. And then, because the product of determinants is the determinant of a product, right, I can write this as the determinant of x minus z times x minus z conjugate. And then this thing here, this is some Hermitian random matrix, which I'll denote H of z. And for us, Hermitian random matrices are much easier to analyze than non-Hermitian ones. So that's the first thing. And I guess to answer Ron's question, this is why it's taking the absolute value is very good for us. Okay. So the second thing is that what we're going to use to actually uncover the branching structure is Dyson-Brownian motion, which is in some sense just Brownian motion on the space of these matrices. So what's going on here is that so first of all, we have some perturbation theory techniques, which are essentially based on the famous forward moment theorem of Tao and Vu, where instead of considering just any random matrix X, we're allowed to instead analyze another model where we add a small Gaussian component to the matrix. So here, G is just IID Gaussians. And T we're thinking of as a time parameter, which will be tending to 0 as n tends to infinity, but you will not really see this note in what's about to follow. So you can think of T as order 1. So, there's a lot going on here, but just what I want to say is that due to some standard techniques, we can instead consider this kind of a model. And the way we're going to construct this model is by allowing it to evolve via a stochastic process. So here, this is just going to be a matrix of Brownian motions. And then at time capital T, X sub capital T will have this distribution here. So this is how we're going to produce this model, which has a little Gaussian component added to it through this stochastic process. And then, the hermitization, so of this model here, I'll just call HT of Z. This is just now going to be the time-dependent X hermitized. Okay. So what I'm going to explain now is how we actually use Dyson-Brownian motion to give us our multi-scale decomposition. So in order to do this, I just need to introduce one more random variable. And so in this tree, one thing we can think of is that at the top, we have some sort of global fluctuation. And as we go down layer by layer in the tree, we're incorporating fluctuations that are on finer and finer scales. So in order to do this, I want to sort of introduce a quantity like our log characteristic polynomial that allows us to go from global fluctuations to fluctuations on finer scales. So let me just call y sub n t of eta. This is going to be, so it's basically going to be the thing we're looking at. So here I have log det, so I can just make this trace log. So this is the trace of the logarithm of h t of z. So far nothing has happened. This is the same thing as we have on the other board, but I'm going to introduce a small regularization parameter like this. And if you write this in terms of the singular values of the original matrix X minus Z, then of course, if you just decompose the trace, This is like, maybe t z I plus eta squared, where these are the singular values of x, t minus c. And then I also have to put some deterministic correction here, right, which is just coming from the circular law. Now it also depends on t and eta, so I won't tell you what it is, but there's just some deterministic term you have to put here, so you still get something that has fluctuations of the right order. Okay. So when eta is 0, we're back to the original thing, and this is very sensitive to the the fluctuations of the very small singular values of ht. Now, when eta is much bigger of order 1, then this is some sort of global quantity, which is not as sensitive to the microscopic fluctuations that are happening. And in this way, this is going to help us get this sort of decomposition on different scales. So the next thing is that I want to use the dynamics. So in order to do this, I'm going to let eta, it's actually going to be a time-dependent regularization factor. And it's basically just going to be a linear function like this. So capital T is our endpoint. When T is capital T, we're at the microscopic level. When T is 0, this is going to be some order 1 thing, so the regularization will be bigger. This CZ is just a constant. It basically has to be chosen it's coming from, so behind the stochastic process here, there's secretly like a complex Burger's equation, which is behind it, and CZ just comes from the characteristics of that equation. So it's just some number which you can compute, but I don't want to write it down. If you like, you can just make this 1, and that's, at this level, everything will be the same. So at this point, I should also say that, characteristics have been used in random matrix theory by many people. So Paul Bourgat in the audience has used this to great effect to study the local statistics of Wigner matrices, and my colleague Jiaoyang Huang has also used it in many different contexts. So with this choice, one can compute the Ito differential of this quantity. So remember that this is the log characteristic polynomial of this time-dependent random matrix, which is evolving via this equation here. So you can compute this differential by the Ito lemma. And due to this specific choice, what you find is that to leading order, it evolves like a martingale. And there's some smaller, lower order thing down here. And in fact, you can compute the covariation of this process for different z and w. And it turns out to leading order be this quantity here. So let me just say that in these two equalities, there is a lot of random matrix theory that actually goes into it. These kinds of differentials, they essentially involve the resolvent of this quantity. So there's lots of expressions that are products of these resolvents. But luckily, my colleague Giorgio essentially knows everything about these. So he can, anything I asked him to compute, he could just tell me what the leading order was instantaneously. And this is just what ended up happening. So that was pretty good. Sorry, and then there's like a 1 plus little o of 1 here. Okay, so what the point of this expression is, and why I'm telling you this, is that if you look at this quantity, so what's going on here is that eta is starting as something big, and it's going to something small. Now, z minus w is fixed. So what basically happens here is that there's some dichotomy, right, where if z minus w squared is much larger than a to t, then we have essentially we have this independence of the increments, right? So this is some martingale increment, so it's like a step in this branching random walk, So there's some independence there. Where z minus w squared is much, much smaller than a to t, then we have, a perfect correlation essentially. Right, now t is starting as a big quantity and is going to some small quantity. So what this is telling us is that, at the start, we basically have perfect correlation of the increments, but when we get far enough down to some branching scale, then we have the independence. And that's the exact same structure that we have there. And this is what's allowing us to uncover the branching structure within our random matrices and actually able to do, get started and do any sort of analysis. Sorry, how much time do I have? 10 minutes, okay. So let me just draw a picture here to explain what's happening. Right, so time, right, it's going from 0 to capital T, and we have our n variable y, right, which is starting at time t is equal to 0, and starts at some large scale, eta naught, which is like t, capital T. And then as time evolves, this goes down to some microscopic scale, yt of 0. So maybe just one side comment. You don't want to go all the way down to the scale of 0. In fact, we do some truncation where you go down to a scale like log n over n or something like that. But for this, at this high level, it doesn't make much of a difference. And now what happens is that, so imagine that we're building up, our random variable y via the stochastic process. Now we're looking at 2 points, right, z and w, right? Each of these, there's a z here. And what happens is that, right, the increments for a certain amount of time, they're perfectly correlated before they actually branch, right? And then, this branching time here, this is just coming from the distance between z and w. And so this kind of a branching structure here is the same as the branching random walk. And this is what enables us to actually say anything about these random matrices. One side comment is that with this sort of y-axis, the increments aren't really contributing equally. So you should graph this on like a log scale, and then you'll get this kind of thing where the increments all are contributing equally. But that's sort of a side comment. Okay. Okay, let's see. Let me use a board over here. So at this point, I can basically just explain what happens with the upper and lower bound. So, on the board, I just erased was our theorem, which tells us that the leading order is like 1 over square root 2 log n. So we split this into 2 things, an upper bound and a lower bound. It's pretty natural, right? So an upper bound, this is going to be similar to the case where we don't have any log correlated structure, where we just are basically doing a union bound. So what these estimates here, so the fact that basically, so if I put z minus w here, if I put z is equal to w here, I have 1 over some linear function. If I integrate this, I'm basically getting a logarithm. So this is where the 1/4 log n is coming from. So the fact that this is deterministic means I can actually construct a very good coupling of y to a Gaussian random variable, right? So for the upper bound, what I can do is that this thing I'm trying to study at time t essentially is equal in distribution to a standard random variable with variance 1/4 log n. And then there's some other term which is much smaller. But the main point is that since I have this coupling, this gets me around the fact of having to try to compute any Laplace transform of this quantity directly, because that's a nightmare. Just due to this coupling, since I can couple directly to a Gaussian, I just know everything about Gaussians. So going through this coupling first instead of directly considering this quantity on the left-hand side, is sort of what saves us, right? So once you have this coupling again, it's just kind of a union bound. So the probability that the max is going to be greater than x, again, the point is that you roughly have n random variables. And you have this Gaussian tail with 1 over square root log n in the denominator. And so you can see that this 1 over square root 2 log n is sort of the critical point. So that's sort of where the upper bound comes from. It's a union bound plus this coupling. So for the lower bound, there's a method in log correlated fields just based on the second moment method. So what you do is you introduce this random variable z, and there's a bit of a lie here, and I'll tell you what the truth is in a second, but it's just the number of points that are just, essentially as large as you want them to be, right? So what you do is you just look at the number of points that exceed your threshold, which is 1 over square root 2 log n, and then you just use the Paley-Zygmunt inequality, which is that the probability that z is greater than theta times the expectation of z, this is greater than 1 minus theta squared, some ratio of the first and second moments. So then the point is that you want to compute the second moment of this quantity and show that it's bounded essentially by the square of the first moment plus a little bit. Now, so there's a couple of lies here. The first is that, there's one which is not so serious, which is that, this is a continuous set, and I want this to be the number of points. So you go to some small grid, some grid of order n in the disk, that's not that serious. The bigger lie here is that you can't directly use the second moment on this quantity. In fact, you have to look at certain high points where in the branching, each sort of level contributes equally. So you have to look at sort of a modified quantity like this, because this thing is not going to concentrate just due to the fact that if you have one high point, then like nearby branches are also big. So you have to modify this quantity a little bit in order to make this work. But the main thing I just want to say is that the second moment method is essentially reducing this to just a question about the joint distribution of the y's, but now only the joint distribution of 2 of them. If we were directly trying to deal with all of them at the same time, that would be a nightmare. But since we're using the second moment, we can just look at the joint distribution of 2 of the y's, which is something we can control because we have good estimates for this covariation process. We wouldn't be able to control a growing number of them at the same time, essentially. So that's one of the main points there. Okay. So it's like 5 minutes or something. 2? Okay, so one thing I'll just say is that we can also do the real case. In the real case, we actually get the same answer. So the real case is a little bit complicated. So what I mean by real case is that if the matrix has real random variables, then there's a symmetry that if you have an eigenvalue in the upper half plane, the conjugate is also an eigenvalue. So here, it turns out the max is actually going to be the same, with the caveat that there is an additional deterministic term that you have to account for in the definition of psi n to still get an asymptotically centered field. And this covariance changes a little bit. Let me maybe stop just by telling the story about the first time I met Jeremy. So the first time I met Jeremy, I was actually, so when I was a graduate student at Harvard, I was working with Yao in his office. And so we were just, talking about something on the board. And then all of a sudden, Jeremy walked in through the door, which was very weird because I was in Boston and he was supposed to be in Toronto, right? So it's just like somehow, God had teleported this guy right here. So I got a chance to meet him. So that was pretty cool. And then we went to lunch And basically the only thing I remember is that, Jeremy was complaining about how the lobster in Boston weren't as fresh as Canadian lobsters or something like that. So let me stop there.
I think there's really a lot of lobster actually.
Yeah. So to get the lower order terms, let me just say that I suspect that I could do the upper bound, but there's some technical difficulties in the lower bound that just kind of make it much harder. It's due to, there was one point where I said, here you integrate to 0. This is a y, and you have to integrate down to some small scale, and then you sort of have to compare something on a short scale to 0. And on the lower bound side, we don't have a good method of doing that, but our method is too lossy to sort of detect it. It would require a substantial, it would require a lot of work, basically. Yep.
Do you need the Ginibre results for your result?
Oh, so that's a great question. No, so what I hoped to state a little bit here is that we're basically directly using this sort of random walk representation for the log characteristic polynomial. And it's basically a direct computation. So we sort of reprove the Ginibre results at the same time. We don't have to rely on that. There is maybe to say that, as I was discussing, in the regularization, we sort of do use a Ginibre result, but it's not a very serious one in some sense.
Okay, well, that's.